Hey, what's up YouTube? Welcome to this part 2 of my short series on water dripping effects using Niagara. In part 1 I explained how I built a CPU Niagara system to create this effect. To briefly summarize, it involved a minimalist state machine to drive two states. One state for when particles are stuck to the ceiling, growing in size and collecting water. And a second state for when particles are big enough to fall from the ceiling and hit the ground, eventually triggering a splash using depth events. In today's video, I'll explain a more dynamic, performant, but also more complex solution using a GPU emitter, distance fields, and a state machine involving multiple states. Particles can now be stuck to any surface and chaotically slide along that surface using a simple friction mechanism. That leads to water droplets naturally gathering around the surface local minima, if that makes sense. Then droplets eventually fall and are converted to a splash particle upon collision. Now this is a GPU emitter, so events are not available, so you have to use hacks to reproduce a similar effect. It's all smoke and mirrors though, and I'll try my best to explain how it's done. Finally, this is all dynamic, right? And it performs quite decently as well. Gotta love GPU-driven particle systems. That being said, collisions are not perfect, because distance fields come with a few quirks, but I'd say it's behaving quite right overall. Now, disclaimers. This is not a tutorial. I won't teach you how to build this step by step, nor will I teach you how to use UE or Niagara. I already have quite a lot of ground to cover, assuming you're familiar with Niagara to begin with. This effect is quite complex, and this video is definitely not beginner friendly. But as usual, I'll do my best to explain as much as possible. I will also do a breakdown of a scriptable tool I built to bake pre-computed data and create another simpler but super duper cheap GPU particle system. Alright, let's dive right into it. So, looking at the GPU emitter, you might be tempted to think there's not a lot to it. But each of these custom modules are packed with stuff, so there's quite a lot to cover. Let's first go over the basics. Here I spawn quite a few particles per second. Particles are initialized, lifetime is set, and particle size is set to 0 at first. I want water droplets to grow in size starting from 0. Next, particles are at first spawned in a circle before being projected onto the nearest surface. And that happens in this first custom module. There's not a lot to it. At the particle's initial position, I query the global distance field to simply project particles onto the nearest surface, if any surface is close by. Else, particles that could not be projected onto a surface are killed. Here I ensure the velocity is set to 0 at first, and I also have a vector per particle to store the nearest surface normal. Finally, if particles were successfully projected onto a surface, and thus alive, I probably still want to kill particles if that surface happens to point upward, or at least not facing downward enough. Droplets wouldn't be able to run down that surface, nor drip from it, so there's no point in surviving at this point. Finally, I initialize the state machine to the sticky state, meaning particles are for now stuck to a surface. By the way, that's just an enum. You can of course create one in Blueprint, then go to your project settings, Niagara, and add that enum of yours to Niagara. You'll then be able to use it in Niagara just like any other variable type. Cool. So a particle can be in one of these three states: sticky, fall, and splash. Thus, on update, for each I have one update module: sticky, fall, splash. And they all are based on the same principle. Say I want to update a particle's position when it's in the sticky state, stuck to a surface. Well, the idea is the following. In that sticky update module, if not in the sticky state, I just forward the position as is, unchanged. Else, if indeed in the sticky state, I can come up with a new position and set it. And same principle in these two other modules, right? If not in the fall state, forward whatever parameter I want to iterate on as is, unchanged. Else, if indeed in the fall state, update it. Does that make sense? Hopefully that's going to make things a bit easier to understand, because these modules are quite dense. Yeah, bear with me, one step at a time. I'll first go over that whole module and it probably won't make sense. But then I'll do a brief summary with visuals to hopefully clear things up a bit. So first, in case a particle is stuck to a surface, I get its velocity and apply gravity. I also add a bit of noise to the velocity, just to bring in some chaos. That's an input vector, by the way. That allows me to specify a made-up noise vector outside this module. So I simply use the curl noise force module configured to not affect particles in any way. It just computes a noise and outputs it, okay? Thus, here I can just get that noise output and voila. That lets me add a bit of noise to the velocity. Next, still iterating upon that velocity, I scale it down to apply friction. Using the particle's normalized age, randomly offset using the material random value pre-computed here, in that initialize module, I sample a curve. And that curve is quite chaotic on purpose, to mimic water droplets sliding down a surface in a chaotic manner. And so I used that value to scale the velocity down and thus slow down particles. Next, the resulting velocity is projected along the last known surface normal. That's at first the vector I set here, using the distance field normal. Next, the particle's position is updated based on that new velocity. The new position, resulting from the velocity integration, is also reprojected onto the nearest surface. Then I do a little safety check here to ensure particles did not climb up the surface after that reprojection and velocity integration. You never know. Finally, the velocity is updated based on the position the particle now has after the distance field reprojection and the position it previously had. I then clamp that velocity to apply a max speed limit. Next, that's a little hack to constrain movement in X and Y. I want droplets to move vertically, mostly, and distance fields can be tricky to work with at times. Computing a velocity resulting from a change in position after distance field reprojection can lead to hectic things every now and then. So this hack helped a bit to keep things under control for this particular effect. Anyway, that velocity is then set if the particle is indeed in that sticky state, else it's unchanged. That's the principle I explained earlier, right? Same here with the position and the global distance field normal. Next, I increase the particle's size over time until it's too big. At which point the particle size is clamped to the maximum allowed size. And then the particle size is set if in the right state. Next, I handle the sprite alignment myself. So if sticky and hanging from the ceiling, I want the water droplet to aim downward. Finally, I update the state machine, meaning if not in the sticky state, remain in that state, whatever that state is, splash or fall, else if the particle is too big and hanging from a surface that is facing downward enough, switch to the fall state, else remain in the sticky state. And that's it for this module, quite a mouthful. Let's take a breather and briefly summarize. Here I handle the velocity. Gravity is added to the particle's current velocity as well as the noise force. Speed is then simply randomly decreased to apply friction. Finally, the velocity is projected along the nearest surface normal. It's next integrated to compute a new position, and that new position is reprojected onto the nearest surface. The particle's final velocity is then derived from the delta position for the next frame. And that's what allows particles to slide down a surface while having some inertia. Rinse and repeat, and you get particles gradually converging towards the geometry's local minima, its lowest local point. Very cool. Now, you could skip computing a velocity and simply offset particles downward before the reprojection. That would create the same-ish effect. The benefit of going with a slightly more complex velocity approach is that you can suddenly make a particle fall from that surface and keep its momentum, and thus have that kind of effect. Particles just don't fall straight down, but have that nice arc. Looks much more natural. Surface tension and whatnot, you know? And while stuck to a surface, particles grow in size. If too big and stuck to a surface facing downward, they simply fall. Now you could also add extra conditions, like if also running down a surface fast enough and changing direction abruptly to stick to the surface, fall as well, or something. The sky is the limit. Niagara, in my opinion, is very well built, and you can build up complexity in a very orderly and linear fashion. I love it. See, something having to do with the velocity, more velocity stuff, even more stuff, and again, and so on. Each step is simple and easy to understand. Anyway, moving on, fall state. Assuming the particle is indeed falling, I simply add gravity. Next, if falling, I want particles to be oriented towards velocity, as simple as that. For the sprite size, I just scale particles along the y-axis to stretch them the faster they fall, quite simple as well. Here I update the position, and then I check for collisions. So from that new position I get the nearest surface. If close enough to any surface, well, there's a collision. Well, not exactly. You see, at first, this is very likely to return the very same surface this particle just fell from, right? Hence, why I check if the nearest surface is oriented upward and if it's oriented differently than the last surface this particle was previously stuck to. If true, only then do I consider that collision valid. Thus, I snap this particle to this hit location. And finally, I update the state machine, meaning if not falling, remain in that current state, else if there's no collision, well, remain in that fall state, else I check the impact velocity to decide if it should switch to the splash state or go back to the sticky state. And that creates an interesting effect. Particles may slide down a surface, fall from a small distance, hit something with little energy, and thus continue sliding down that new surface. So to summarize, there's not a lot to do in that fall state, right? Apply gravity, check for collisions, and do safety checks to reject false positives, and update the state machine to go back to the sticky state, continue falling, or switch to the splash state. Speaking of, if indeed in that splash state, velocity is first set to 0, I then increment a timer to know how long the particle spent in that state. Based on that splash timer, I scale the splash sprite up. Keep in mind that the same particle, so its scale, once in the splash state, is a totally new scale. It's suddenly much bigger than what it was in the fall or sticky state, right? Finally, I make sure the splash sprite is aligned towards the hit normal. That normal being the global distance field's normal output by the previous update module. And that's it for the update splash module. So, because this particle is recycled and has, I might say, many lives, sticky, fall, splash, that single sprite may need to have a specific look for each state. And that's done using a material dynamic parameter. I first forward the state the particle is in to the material, and the normalized splash time. That's a 0 to 1 value based on the splash time and an arbitrary splash duration. I can then get that information in the material and do stuff with it, but I'll get back to that later on. Moving on, I also apply an offset to the particle's position based on its state. So if stuck to a surface, I offset the particle from that surface based on the sprite size, so it doesn't clip through the mesh. Same for the splash state, and that offset is lerped to smooth out the state transition. It's then added to the position to set a new position I called render position, and the sprite render's position binding is tweaked to use that render position instead of the default position parameter. Now that offset thingy is a bit of a hack, to be honest. I'm not too fond of it, but meh. There are infinite ways to create such a water dripping effect, okay? At this point I'm merely showing what worked for me, but feel free to do things differently. Anyway, finally, particles life management. If in the sticky or fall state, I simply ensure the particle doesn't exceed its lifetime. Else, if in the splash state, the particle's lifetime no longer has any effect, because I want to ensure the splash animation is done before killing the particle. And that's it for the particle system. Oof. Now, regarding the sprite material, let's take a brief look. I'm using deserved masked opacity. I'm also using the dynamic parameter node to read the values sent by Niagara, right? So if the particle is in the splash state, I play a simple splash flipbook animation using the forwarded splash time. Else, I just compute a simple spherical mask to drive the opacity. The masked opacity is also tweaked a little bit during the shadow pass to prevent the splash particle from drawing too big of a shadow. Next, this material uses world space normals. So for the splash, I simply convert the local z-axis to world space. Else I compute a spherical normal for the water droplet. Finally, you may try adding a bit of desired pixel depth offset, and voila! That's how I created this cool GPU Niagara system. Now, what's next? Well, I got two versions of that effect. The one I just explained has this simple splash effect. That water droplet sprite is sort of converted to a splash sprite upon collision, right? But ideally, I'd want to spawn extra particles upon collision, like I did in my CPU version, right, using depth events. Sadly, events are not supported in GPU emitters, so I had to cheat big time. I made a second version that uses a mesh renderer to render one of these three meshes, and which one is rendered is randomly decided upon particle spawn here. And you see, these meshes are a bit special. They are made of a plane for the particle sprite, right? But they also have extra planes for the extra sprites to spawn upon collision. And these are differentiated from the main sprite using a second UV map. The vertical axis is used as a mask. If above 0.5, that's the main droplet sprite, else that's the extra droplet sprites. And then these extra droplets have somewhat random UV values to encode a random splash direction, more on that in a second. So in that emitter, I no longer care about the sprite's alignment. I need instead to compute the mesh's orientation. So first I figure out what is its forward vector, depending on the particle state, and second I get the view vector. Finally, a quaternion is derived from these two unit vectors, that's it. I also send the mesh's material extra information. I still send that same information using the dynamic material parameter, right? But now using the dynamic material parameter 1, that's another binding, yeah? I send the material some more information. The heat normal is sent as a compressed quaternion, and there's the extra droplet scale, stretch and whatnot, right? So the splash can be fine-tuned and even randomized per particle. That means in the material I now have access to that extra information, as well as the information I encoded in UVs, like I explained, to distinguish the main droplet from the extra droplets. And thus I can do some world position offset shenanigan. Now I'll be brief here. I've covered these vertex shader tricks over and over in previous videos, so feel free to check out my YouTube channel for more information. Basically, I can apply a ballistic offset and have that offset be applied only on the extra droplets using that UV mask I previously mentioned. The X and Y direction can be randomized in many ways. Here I merely used data encoded in UVs to generate a pseudo-random direction. It's sketchy, but whatever. Droplets can then be scaled up, made to look at the camera, and collapsed if the particle is not in the splash state to avoid overdraw. And the rest is somewhat similar to the first material I explained. And that's how I faked these splash water droplets. They are embedded into the mesh, hidden until there's a collision and thus a splash. And performance remains decent. Meshes are instantiated, vertex count is slightly increased, but that's not too bad, and overdraw is limited because vertices are collapsed using world position offset. Now, this is a GPU emitter. We can spawn thousands of particles. Yay, it's running great, but this is not free, right? All things considered, it's quite a complex system. It has quite a bit of logic just to create water droplets, and distance fields are not necessarily that expensive to sample, but it's not free either. Also, that's the price to pay for an effect that can be dragged and dropped anywhere in the world and react dynamically to changes in the environment, right? But maybe you just don't care about that. Maybe you just like to add a few water dripping effects here and there and don't care about dynamism. Yeah, that was my thinking as well, hence why I tried a totally different approach. To be honest, I merely wanted an excuse to showcase Unreal Engine's Scriptable Tools, because I have not yet had the opportunity to do so on my channel. So first things first, enable the Scriptable Tools plugin. You'll be able to create a Scriptable Tool blueprint, and today we'll take a look at the standard click and drag class. that class comes with a couple of interesting events: onScript setup, onScript tick, onScript shutdown, and a few more that are specific to the click and drag subclass, like onDrag begin, onDrag end, and onDrag update position. There's also a function you'll likely want to override, test if can begin click drag. Alright, so onScript setup is likely where you want to add properties. A properties set is another blueprint class specific to the Scriptable Tools plugin. It acts like a variable container, basically. So you create one, add all the variables you'll need when using your tool, and then in your Scriptable Tool blueprint, on Script Setup, you simply call this addPropertySetOfType function. Specify your property set and maybe give it an identifier as well. Next, it's usually considered best practice to cast to your property set class so you can cache that object to easily access its properties in this blueprint. You could then add event listeners in case properties are changed and whatnot. Pretty cool. So that's what allows a tool to have settings, or properties, I might say. And how you get access to these in the script blueprint, okay? Next, these drag events and this drag function all give you a ray struct to work with. So I like to create a little helper function to convert that to a hit result, meaning I just get the ray's origin and direction from that struct to do a line trace in world space and return the hit result. That's pretty much it. So in that test function, if I hit anything at that click position, I return an input ray hit node and I forward the distance and hit actor. Else I return a ray miss. Essentially, this returns true, this false. Thus, the onDrag begin event is called when true is returned from that test function. And again, I convert that ray to a hit and cache the hit location in a vector. That's where I clicked in world space, right? Where the click and drag starts. So for now, my goal is to rebuild this effect, okay? I want to define an area given a start and an end point. And that area's radius is simply the distance between these 2 points. So I made a float called radius in this property set, so I set it to 0 at first when the drag begins. Which means if you think of that radius as a constraint, the endpoint would have to be located at the start point for that area's radius to be 0. Next, I create a gizmo, and that's a cool feature that comes with Scriptable Tools. Give it a unique identifier, a transform, and options. Here I only care about offering the user the ability to translate the gizmo. Now, if that function failed though, it probably means the gizmo already exists. So I just override its transform, okay? So now if I click on something, a gizmo is created at that location. Cool. Next, there's an event called onGizmoTransformChanged. That's pretty straightforward. That's called when you tweak the gizmo in the viewport. So if that happens, I just want to override that origin variable of mine and have it be located on the gizmo. Next, on drag update position, I call that ray to hit function again and cache that position. And that allows me to compute the distance between these two vectors and thus come up with a radius. And actually, let's do that upon drag end as well, to ensure I always get the latest position. Then on tick, let's flush persistent debug lines and draw a circle. And voila, click and drag, move the gizmo and it works. Click and drag again and yeah, everything works. So that's the gist of it. That scriptable tool essentially allows me to select an area where I want to spawn droplets. And I won't go into too much detail here, but the idea is very similar in principle to the very first CPU system I explained in my previous video. I assumed that effect was entirely static and pre-computed to be as cheap as possible. So the idea here is to do a bunch of line traces in that circle to find a valid ceiling at random positions. Next, do line traces from these positions to get the ground and compute distances. And from that, you can compute FreeFall durations. You can even do cool things like, upon line trace, check if the actor or component hit has a tag for water, to drive a different splash effect for drips that hit a solid ground or water, right? Maybe cache the hit normals as well, and that's pretty much it. Make a blueprint struct to gather that information into an array and you're halfway there. The goal next is to write that data into a tiny texture that can be sampled in Niagara. And that's nothing too complex in practice. Create a render target. For each drip, add a pixel in the horizontal axis. And for each data to store per drip, add a pixel in the vertical axis. Well, I mean, you'd work with RGBA channels, right? So you could pack 4 data per pixel. And even more if you bitpack some data and whatnot. So in the end, it depends on how many floats you want to store per drip and how you do things, right? Also, keep in mind it's always best to work with power of 2s. So if you have 100 drips to bake, it would likely be best to have some padding and work with a 128 render target, yeah? So having created a render target, the next mission is to write stuff into it. And that's nothing too complicated, thanks to Niagara. Create a GPU emitter. Create user parameters for float 4 arrays and a texture render target as well. Next, create emitter parameters for each of these. And get that render target size in X, that's how many drips to bake. Next, create a simulation stage and iterate over that count. And for each pixel in X, get entries in these arrays and write columns of pixels into that render target, if that makes sense. And that's basically it for this emitter, so there are 2 remaining steps. 1, it needs data to work with, right? 2, it needs to exist in the first place, to be spawned in the world. Let's handle data first. So in blueprints, you then have to convert that struct array into vector for arrays. Personally, I made 2. The first array, thus the first line of pixels, contains the XYZ position and distance from the ceiling to the ground. And the second line of pixels contains the X and Y hit normal, hit mode and a random float. Next, that Niagara system needs to exist. Thus, upon script setup, I spawn a Niagara actor. I set its system asset and forward the render target I created. Next, on tick when tracing for drips, I send the vector for arrays and advance the simulation. That almost drove me crazy, by the way. It seems that the engine is put in some kind of pseudo pause when a scriptable tool is set up, or that there's a bug somewhere that prevents the Niagara system to be properly initialized when spawned with a scriptable tool. I don't know, but that Niagara system refused to work. And then I had the idea to call this function and it solved my problem. I ran in a circle for 3 days figuring this one out. I almost went nuts. Anyway, at this point, that Niagara system should have all it needs to do its thing, and that render target I created should contain the drips data. Thus, upon script shutdown, I compute that emitter's bounds, and I convert that render target to a static texture. Make sure to use nearest filter, super important to prevent pixel interpolation. And here I spawn a blueprint that owns the actual Niagara drips effect and makes use of that texture. So I have 2, right? One system that does the baking, one that is the actual VFX. The first one, having at this point completed its mission, is destroyed upon script shutdown. And the latter lives on in that blueprint. Now sadly, it's a somewhat complex system, so I fear I can't afford to do a super thorough breakdown, so I'll remain brief here. These all are GPU emitters. Drips, impact droplets, impact water, and that one, by the way, is only enabled if a water actor or component was previously detected during line traces, remember? And finally, impact splash. They should sound somewhat straightforward, right? That's the main water droplet, that's the extra droplets spawned upon hit, that's the splash, and that's the extra splash spawned upon hitting a water surface. Now, the thing to note here is that they all use a spawn burst instantaneous module, meaning they all spawn particles just once and that's it. Yet the effect is ongoing, right? So what's happening here? Well, each emitter reads the texture that contains the baked data, and checks how many pixels it has in the horizontal axis to deduce how many particles to spawn. 1 per row of pixels. Or multiple particles per row of pixels for the droplets. Upon particle spawn, then each particle samples the row of pixels corresponding to its index. And then it decompiles the data to rebuild the information that was packed into these 2 pixels. See, position, random value, hit mode, and so on. Just like it was sent to that Niagara system used to create the render target, and thus that texture. And so, from that baked data, I know these particles start and impact positions. Thus, I can deduce how much time this particle will be free-falling before hitting the ground or the water. Thus, it's completely deterministic. Which means, for each emitter, I can come up with a shared animation timeline. Let's say each droplet is first stuck to the ceiling for 1 second, then droplets fall from the ceiling and thus are in that free-fall state for a certain duration. And that varies per drip, per particle, right, depending on the ceiling height. Then I assume the splash animation lasts 2 seconds or something, and then it loops. So I have a timeline to work with, okay? And that's precisely what I do in Niagara. During update, I increment that anim time, check if it should loop based on the anim duration, and if so, reset the time. And from that time, I can deduce in which state the particle is in. Is it in the sticky state? If not, is it in the fall state? Else it must be in the splash state. And then I'm using the same principles I explained earlier in the video. If in this or that state, drive the particle's position, sprite size, and so on. But the cool thing now is that I can spawn extra particles, like say 4 more particles per drip, okay? Then do the same thing, do that anim time thingy to figure out in which state the particle is in, and drive the sprite size to collapse and hide these particles unless in the splash state. And that's what allows me to spawn extra droplets and splashes upon collision and fake death events. They all are pre-spawned, just like the drips, and they all share the same animation timeline because reading from the same texture pixels. Thus, because all components of the entire particle system are in sync, I can make you believe droplets are spawned upon hit when they are just hidden, waiting for the timeline to be in that splash state. Hopefully that makes sense. Sadly, I don't feel like doing a 2 hours long video to further explain this, so this will have to do. I'll let you take a look at the files if you want to investigate things some more. The project is available as a tier 3 reward on my Patreon. Voila, that's the end of this 2-part series on water dripping effects. I've covered CPU systems, GPU systems, some were static and pre-computed, and some were dynamic. And they all have their pros and cons, just got to learn when to use which. I also took a brief detour to give Scriptable Tools a short introduction, so yeah, hopefully you learned a few things here and there. Thanks for watching, thanks to all my patrons for the incredible support. I can only do these kinds of studies and videos because of you, you're the best. Consider leaving a like and subscribing to the channel. Alright, I'll see you in the next video. In the meantime, take care of yourself. Bye bye!